Not every optimization problem leads to a quadratic equation that you can use x equals negative b over a to find the maximum or minimum point. One example of this is, imagine I have a square piece of cardboard. It's 20 inches by 20 inches. And I want to convert it into a three-dimensional box. There are various ways to do this, but one way to do it is to cut a square out of each corner. I'll call it x by x square. And I cut these pieces out, so I get this big like plus sign looking thing. And then I fold it up so that this square in the middle becomes the base and the other four things become the sides. So this ends up being a box that has no top. It ends up looking like that, open top box. Well, this side here ends up becoming this side. This side here ends up becoming that side. And this side over here ends up becoming that side. So the dimensions of this box are x, and this red line here is not the whole 20, it's 20 minus 2x. And the blue line is also not the full 20, but you take away these two x's. So the volume of this box is calculated by x times 20 minus 2x times 20 minus 2x. And you don't have to do this, but I just want to show you that if you were to multiply this thing out, it would be 4x to the third minus 80x squared plus 400x. And that's a cubic, and cubics generally have like an S shape to them, and this one does also. It ends up looking something like that. Now, the domain of this function actually is from 0. The smallest square I can cut out is 0, and the biggest square I can cut out is actually 10, because at that point it fills up the entire thing. So really the only piece of this curve that's relevant is this piece between x equals 0 and x equals 10. And the volume, depending on what x is, the volume of the box changes. So the question they want to know is what would maximize the volume, and for that you could graph it on the graphing calculator and we'd find this maximum point. And it ends up becoming 3 1/3 for x and about 594, I think, for y. So you have to pop this into the calculator. It's not a quadratic. You can't do x equals negative b over 2a. However, there is a way when you have a cubic equation. Here's an example of a cubic graph. It's y equals x to the third plus 3x squared minus 24x. There is a formula for finding the coordinates of the turning points of a cubic curve, and I'm not going to explain where this formula came from because the easiest way to explain it requires calculus. But I'll just say max slash min. Actually gets you both at x equals, check this out, if this is ax to the third plus bx squared plus cx plus d, the formula is not negative b over 2a like it was for quadratics. Instead, it's kind of a funny formula. It's negative b plus or minus the square root of b squared. Looks like the quadratic formula, but it has a 3 here, 3ac over 3a. So that's a weird formula. It's like someone forgot the quadratic formula, but that is the formula. So when I apply it to this situation, I get negative 3 plus or minus the square root of 9 minus, ends up being plus 72 over 3. That becomes 81. That becomes 9. So 3 plus 9 over 3. Minus 3 plus 9 over 3 is 6 over 3, so it equals 2. Or minus 3 minus 9 is minus 12 over 3 is negative 4. And those end up being the x-coordinates of these two turning points. So that's a formula. You memorize that formula. Kind of a funny formula, it's like the quadratic formula. So I could go back to this other question, the box question, and the volume, which I'm calling y, is 4x cubed minus 80x squared plus 400x. And if I do the formula, I get negative b plus or minus the square root of b squared 6400 minus 3 AC, which is 4800 over 3a, which is 12. And if you work that out, you will get, when you use the minus, because remember that curve kind of looked like this, so we only cared about the one on the left, you will end up with 3 1/3. Okay, 3 more problems for this lesson. Here's an optimization question where there's like there's a beach and there's water and there's somebody out here who needs help, and you are at the beach somewhere over here. And you can run faster than you can swim. You run 5 miles an hour and you swim 2 miles an hour. Swim. And the question is, what route should you take best to get from where you are to where you want to be? You want to get out to that person. Here's some more facts. You're 2 miles from the beach this way. They are 3 miles or from the shore in this direction. And the distance from here to here is also 3. So this isn't drawn that well. It's a scale. Now you might think, well, maybe I should just run straight and then swim the rest of the way. That ends up taking about 2.5 minutes or hours, the way this is. You might think I should run diagonally and swim this short distance. That ends up taking about 2.2 hours. So it is faster to run diagonally across, but maybe there's a faster way than both of those, somewhere in the middle, or maybe it's exactly in the middle. Well, there's a way to figure that out. I'm going to pick a random spot on the shore, and I'm going to call this distance x and this 3 minus x. And I'm going to create these two right triangles. Now the amount of time it takes to run from the green to this point and then to swim from that point to the red, well, the amount of time is distance divided by time, but there's two different legs of this trip. So this hypotenuse here is the square root of 4 plus x squared, which means the amount of time to get to the shore is 4 plus x squared divided by 5. Now I have to swim. Well, how much do I swim? Well, for that, it's the hypotenuse of this other triangle, which is the square root of 3 squared plus the square root of 3 minus x squared. And I'm just going to leave it like that. And it's going to be over 2 because I swim slower. Now this would be a pretty annoying thing to simplify. The good news is that we don't have to. We pop that into the calculator and graph this thing where t is kind of like my y value and x is this distance here, and it ends up becoming a thing like this, and then we just use the calculator minimum function to find that at 2.09 it takes 2.15 hours. So this is the setup, and we do not have a fancy way to calculate that the way we did for cubics or for quadratics. We just pop it into the calculator. Another scenario is I want to make a page of text, and the text So there's two rectangles. The text rectangle has dimensions x by y, and the margins are going to be, the left and right margins are going to be 1.5 on each side, and the top and bottom margins are going to be 1 inch on each side. And if we're told that the text is 24 square inches of text, they want to know what dimensions for x and y would minimize the size of the large piece of paper. Well, the area of the large piece of paper is x plus 2 times x plus 3 times y plus 2. So I have a 3-variable equation and a 2-variable equation. If we solve for y in terms of x, 24 over x, and then substitute that in, x plus 3 times 24 over x plus 2. Now if I graph this thing right now, I get a strange shape, and it looks like a parabola, and the minimum using the calculator is 654. So that means that it's a 6 by 4 rectangle, and that this big piece of paper is going to be 6 by 9 with an area of 54. Incidentally, if I multiply this thing out, I would get 2x plus 30 plus 72 over x, meaning this graph is actually part of one of those slant asymptote questions. Okay, the final question is, I want to make a cylinder, and I want the volume of the cylinder to be 355. And I want to minimize the surface area. So what's the smallest surface area I can have to have the cylinder have a volume of 355? Well, for that we're going to need some formulas. Volume of a cylinder is pi r squared h. And the surface area of a cylinder is 2 pi rh. That just is the lateral surface area, not including the top and bottom. Sometimes these things don't have tops and bottoms, but this time it does have a top and a bottom. So plus 2 pi r squared, that takes care of the top and the bottom. So notice how, and since I know the volume is 355, I'll put it there. So once again, I have a 2-variable equation, r and h, and a 3-variable equation, surface area, r and h. Now, I'm going to choose to solve for h in terms of r. It's 355 over pi r squared. I could have also solved for r in terms of h, but since there's only one h here, it's better. Just call this s. S equals 2 pi r times 355 pi r squared plus 2 pi r squared. I can do some canceling. The pi's cancel, one of the r's cancel. I end up with 2 pi r squared plus 710 over r. That's my equation. So if I graph, if I make the r into an x and the s into a y, I get a kind of unusual looking graph. It's actually a graph with a parabolic asymptote. It's a pretty hard to picture actually, but regardless, it looks a little bit like a parabola, at least on that side. And if we find the minimum point, we find out that when x is 3.8, which is the radius, the surface area ends up being, I think, 278. So those are some new scenarios. We have the this cylinder one, this page formatting one, this running to save someone who's drowning or whatever, they need help, they're stuck on a boat, they have a couple of hours to wait but not that much more, you want to get there as fast as you can, And also in this video I showed how there's this formula for finding the turning points of cubic equations that comes in handy for the box question. Well, that's optimization day 2.